السلام عليكم.
وعليكم السلام.
هل نبدأ؟
بسم الله.
بسم الله. السلام عليكم جميعا. أعتذر على التأخر طفيف. أتشرف جدا بالحديث إليكم اليوم، خاصة وأني كنت طالبا مثلكم منذ سنوات. مشاركتي اليوم مشاركة تجربة عن معلومات وددت لو كنت أعرفها لما كنت طالبا. يسعدني جدا أن ألتقي بكم جميعا. إن شاء الله تكون مرات قادمة نتقابل وجها لوجه. بداية أود شكر البروفيسور محمودي على هذه الفرصة مشاركتي اليوم. عنوان اللقاء عن نانو إلكترونيكس. هي مشاركة تجربة، ويمكننا الحديث عن تفاصيل أكثر عن أي موضوع عن أي موضوع سأذكره خلال هذه المحاضرة، ويمكنكم مراسلتي للحصول على معلومات أكثر. يمكننا النقاش عن الموضوع. أود فعلا أن تكون محاضرة باللغة العربية، ولكن باللغة الإنجليزية ستكون أنفع، خاصة وأن المدرسة تتبنى اللغة الإنجليزية. So thank you very much for this opportunity. So my talk today is going to be about nanoelectronics in general, and we will talk about beyond Moore's law. We will get to know Moore's law and how nanotechnology is present, how it's leading the innovation and the reshaping the semiconductor industry, and especially for the most advanced markets, which are the AI and high performance computing products. So today I will try to take you into a journey into the different aspects of the nanotechnology in the semiconductor industry, or more globally, the electronics industry. And we will have the chance to discuss many topics related to it. So before starting, we can find, I'd like to say that the nanotechnology or the nanoscale is present in different segments. You know better, of course. So we can find it in medicine, in drug delivery, in aerospace, in water cleaning, water recycling, energy. But today we are going to talk about it in a segment in which the nanotechnology is more present, which is the electronics in general. We call it microelectronics or semiconductors. All these represent the electronics. So microelectronics, because the name was given to the electronics when the micro scale was dominant in this electronics. And in the recent years, we have seen a new emerging scale, which is the nanoscale, advanced in the application of nanoelectronics or semiconductors, to be brief, and for which many aspects are supporting this nanoelectronics industry. We have the characterization, we have the modeling of nano devices, and many technologies. Today, we are mainly going to focus about semiconductors and also silicon, which is the key material for the electronics. So now, nowadays, we can find the microelectronics in our phones from generation to another. We can see, we don't feel it, but we feel, but we are not aware of the impact of nanotechnologies in the new generations of the iPhones, for example, or the laptops. Even with the new generation of electrical cars, we have more silicon content. And far from us, currently in the recent years, we started to use AI. And by using AI and implemented in data centers, we are using more and more the nanotechnology scale in electronics. So the title of the talk is about Moore's law, and to define it quickly. So Moore, or is Gordon Moore, the co-founder of Intel, So in the 60s of the last century, he has written a paper about the future of the integrated circuits, the ICs, or what we call. So he observed the evolution of the market, and he said that this is the original chart from his paper. So he said that the number of transistors is doubling each 2 years. So from each 2 years, in the same space, we have more transistors. So why do we use transistor, etc.? We will know it in the next slide. So, and his observation stayed for a long time, and currently, starting from 2020, the industry of semiconductors is discussing whether the Moore's law is dead or not yet. So here is his originality law. He says that the number of transistors in IC within an integrated circuit doubles each 2 years. So he proved it with the available data in the 60s, but now we can see in the chart at the left that these are all the products, starting with the Intel product, one of the leaders in this market. And here we can see that there is a line of growth for the number of transistors within an integrated circuit. But the problem now today is that the question is whether Moore's law is dead or not yet, because we are facing some silicon, some physical limits. We cannot put finer sizes of the transistors. So now the industry is talking about beyond Moore's law, whether we can use the silicon for more computing, or we can use photonics and many other alternatives, especially that we are living in the era where we have huge increase in demand for computing and data. And with the available hardware in terms of CPUs or GPUs, processors in general, we will not be able to provide enough computing power for such systems. So this is Moore's law. But before talking about Moore's law, there are many industries who passed from the mesoscale to microscale and the nanoscale. So today we are going to talk about the nanoelectronics especially. So when the industry started with millimeters. The first transistor had centimeters even in the size of the transistor length of the gates, etc. Then it passed to the microelectronics. Here we started, the industry started the mass production, and we started to receive more electronics in our lives, starting from the TV, the electronic cars, and the computers. And here we started the new revolution of the IT, the new era. And currently, and the industry kept pushing the micro scale to the nanoscale. And today we have some advanced products based on the nanoscale. The atomic scale can be pushed for new industry revolutions like the quantum or the optical photonics hardware. But for the nanoelectronics, it is currently balancing between the microscale and the nanoscale. And we can use both of them to develop the advanced products that we can see in our life today. So when we talk about electronics, we talk about semiconductors. I believe that you are aware of the definition of the semiconductors. So briefly, we have three kinds of materials: metals, semiconductors, and insulators. And this segmentation is based on the gap between the valence layer and the conduction layer. And for the semiconductors, they have a very small gap between these two layers, and this small gap can be conductive sometimes and dielectric in other times. So depending on the doping parameters, so we can engineer the semiconductors to change or to tune the parameters, physical parameters of the semiconductors. One of the most known semiconductors is silicon, but in the recent years and decades, another alternative of silicon is being used and more in our daily life, which is germanium. And these are the basic elements from the periodic table, but by combining many dielectric elements in the periodic table, we can develop also new semiconductors. But in our daily life, in our phones, in laptops, and any electronic device, we are using the silicon inside it. And of course, we can dope it and change it to our use. But today, we are going to focus only on silicon. So by silicon, when we talk about silicon, we can find it in the sand. We can process the sand to obtain the silicon. Then we can form these lingots of silicon. We can slice them to obtain what we call the silicon wafer. It is a round shape of silicon made of 100% of silicon, depending on the doping and the orientation of this silicon. We are going to add deposit some layers, some metallic layers, some dielectrics to copy the design of the processor. So we are in the industry today. We use the silicon wafer as a base to copy or to do the photolithography of the design of transistors. So we are going to design we pass from the design of the electronic circuits of the processor inside. We are going to deposit all the materials to have the same design on a wafer on this round shape of silicon. Then we dice it to have a small piece of silicon made of many transistors, and then we need to pack it and have it inside a chip. That's what we call the integrated circuit. So in this small piece of silicon, we have the design of transistors, and then we interconnect this piece of silicon with the design to the rest of the elements on a printed board, or what we call the PCB. So it started with the transistor. So the transistor started with the invention of the two contact points. So here we have two metals connected to one end. Then we have one end at the end. Here is this symbol of transistor, the basic one. We can have different symbol of it depending on the function. We can use this transistor. We basically use it to amplify or to switch the electronics signals. So it is the element at which we have the binary 0 and 1, which is the basis of computation today, and how to convert the algorithm to computing software. So this transistor, as you can see, its invention started in the 1947, and then its size started to decrease with the time. So one of the benefits of using the nanotechnology in the nanoelectronics is to be able to do the miniaturization of the product. So we are going to see many examples of the miniaturization in semiconductors, but today we are able to put more than billions of transistors within 1 centimeter square, 1 square centimeter of transistors. This is enormous. Here we can see that the scale of transistor passed from centimeters maybe to millimeters, micrometers, and this is nanometers. So transistor is the basis of computation and to be able to apply the binary 0 and 1 within. It is the hardware enabler of the approach of binary 0 and 1. In this slide, we can see the evolution and the timeline of the transistor. So it started in 1947, and with the time from a decade to a decade, this technology gained more and more in the maturity, and in the end of the 50s, we had the invention of the first integrated circuits, the first IC, which allowed to have more electronics and more silicon content in our daily life. So, and from the 1965, Gordon Moore proposed Moore's law. He shared his observation about the number of the transistor that doubles from each 2 years. So it allows to have a better performance with the same size for each 2 years, and you can imagine the evolution from 65 and before to now. How many performance stages has passed the electronic industry from the 65 to today, 2025. So, and of course, each time the industry through the evolution passed via different architectures. It started with an architecture, but today the dominant architecture is another story. And the question here is whether the industry stopped developing new architectures. No, the industry and all the research society is continuing the effort to develop and propose new architectures in order to provide to the electronics industry more and more solutions to be able to handle the enormous quantity of data and computing that we need today and in the future years. Here we can see many architectures and many products developed based on the transistor. So we can see some major milestones, like the first million transistors, and then the first billion in transistors, and now we are talking about 100 billions within one chip. This is enormous. So this is the first image of the integrated circuit developed at Fairchild, which became Intel later. So you can see the size of the first integrated circuit. So it's based off two transistors. Now, many decades and years later, here is one of the most advanced chips today, developed and designed by NVIDIA. So inside this chip, we can find more than 80 billion transistors. So it is an enormous evolution from the 60s of the last century to today. So we are going to focus today on this product mainly because we have the tear down of this product. But from 2024 to today, 1 year, NVIDIA has announced two chips more advanced compared to this one, and we are going to see how such kind of advanced chip is made, and all this evolution from two transistors, maybe in 5 centimeter by 5 centimeter, to a chip of 5 centimeter by 5 centimeter, has been enabled by all the efforts of people coming with nanotechnology background and the intention to miniaturize all the electronic products. We will see that the nanoscale has been implemented at different parts of the supply chain of fabrication of such devices. So this is very known picture of 250 megabytes hard drive. It is very heavy, so one operator cannot hold one hard drive of 250 megabytes. But today, in all your smartphones or laptops, you have more capacity, more memory capacity compared to this image. But you cannot only hold it, but you can hold maybe thousands, hundreds or thousands of such of similar capacity. Today, this memory is commercialized. It is for consumer from SanDisk, a memory player. They succeeded to develop 1 terabyte SD card for our daily life, and its size is very, very small, and its weight is has been reduced hundreds and thousands of times. This example also has been enabled by the nanotechnology and the miniaturization efforts. In the previous slide, the efforts were made in the logic and computing, which is the most advanced and the most important. But the memory also is important to enable the computing and to have all the data storage and different kinds of memory storage. So this is commercialized. Maybe you have seen it, but the industry has more developed and more advanced products, which are called the HBM, high bandwidth memory. So it has the doubles and doubles of the memory capacity of this SD card, but it is not used separately. We can find it inside the most advanced chips today, and we will see why in the next slide. So we talk about the semiconductor industry, we talk about technology and electronics. So here in this prism, inverted prism, we can find all the technology industries, from consumer to telecommunications, automotive, AR and VR, personal computers, industry, aerospace and defense, and also data centers. Here you can find many players, known players like Apple, Facebook, Microsoft, and many other Chinese players. So these are the end customers, the sellers of the end products. But most of them do not fabricate the devices they sell. But beyond it, we can find some electronic and system players. So they allow to the previous players to do the assembly of their systems and prepare the devices for them. And today we are going to talk about the semiconductor devices. The semiconductor, what we mean by semiconductor devices: the memory, the CPU, the processors, and the sensors. All of these are considered as semiconductor devices. And of course, the semiconductor industry, it has a market value of 530 billion. This industry has a bigger bigger revenues compared to many countries. So it is in the trajectory to reach 1 trillion by 2030. So this industry is very important and very big compared to other industries, and in terms of economics, it is very important. And we will see why some government today are focusing on this semiconductor industry as strategic. They are all of the big countries started to develop local strategies to have the production of semiconductors inside their countries. So this is very important. And of course, we have other supportive industries like equipment and material. They are important also for semiconductor manufacturing, and also some software, EDAs, electronic design aid, and also IP for the semiconductors. Here we can see the different players, different segmentations of the players. We have the end users or the sellers of the electronic devices, but the semiconductor industry is made of kind of unknown players. we have Intel. Maybe most of you know Intel. We have NVIDIA, Infineon, NXP, foundries like TSMC, and many others. If you know one player or two, but most of the players are unknown because they are not in the marketing on that. Despite they are the enablers of our daily life electronic devices that we use. And in the lower part, we have some EDAs and some companies allowing the semiconductor industry to have high volume manufacturing with high yield. So these are some numbers and the evolution of this strategic industry, semiconductor industry. So it passed from 6 years ago, it was the market value was at 400 billions. In the last year, it was 600 billions. It is an enormous growth in 6 years. And the goal of the industry is to reach 1,000 billions or 1 trillion by 2030. And we have here, we can see in colors, the different colors, the different markets served by this semiconductor industry, from mobile, consumer products, computing, and defense, automotive. All of these are enabled by the semiconductor industry. And without the semiconductor industry, such markets cannot evolve. So here is the first transistor with, so the transistor has basic architecture made of the source, the gates, and drain. So here I go back to the transistor, and through the years and decades, the transistor has faced some limitations, and it had the obligation to change the architecture to keep the same function, the same role, but with different architectures. So here, for example, starting from 2011 to now, we have seen different architecture of these three elements: the gate, the drain, and the source. So here we had this is the one transistor, and it passed. This is the planar FET, the field effect transistor, and it has been developed to the FinFET. It is not planar; it is smaller, so it allows you to have more transistors in the same area on the same space. And then the next generation, which has been commercialized starting from last year, which is called the GAFET, the gates all around. So you can see that the size has been reduced from the FinFET to the GAFET, and we started to use nanowires. It is so the material. If we talk about the scaling of the material, we can pass from bulk material to thin films, and in the thin films we can have different nanosheets, nanowires, and all these kinds of nanoforms, nanoscale. We can find them in the heart of our devices today, and started by the transistor. So here we can see the gate and the source and the drain, but these are nanowires. So is this enough for our computing, our needs today? No. The researchers and the companies continue to develop new architectures with smaller sizes and better performance, because you need, if you pass from generation to the next one, you need to reduce the size and enhance the performance, and also enhance the energy efficiency. So if we compare the energy consumption of one transistor or one processor a few years ago, and we compare it now with the current consumption of our daily use computers today, we will see that the energy consumption has been reduced, and also the computation power has been tripled or more than that. So these architectures of transistors are being proposed for the next generations, but not all the players, not all the companies are able to develop these companies. The number of people working on transistors or the new architectures and devices bypass thousands or millions of people working on that. It is not the efforts of one person. So this is an additional benefit of having nanotechnology. You cannot develop everything alone, but you need some effort to develop all these new sciences and the new architectures for all the humanity. So this is the roadmap for the architectures for transistors. But inside the processor, for example, and CPU or GPU or others, we have the transistors, but they are very small. But how can we connect these transistors and calculations of 0 and 1 to other elements, for example, the memory? For that, here at left, you can see here we can at the bottom layer we can see the transistors. So the transistors they have a very thin metallic layer, and we keep adding metallic layers with increasing thickness to be able to connect them to the printed board, the PCB, and so if you have the computation instruction at the bottom layer, it has to pass by all these copper layers. They are made of copper to reach the interconnection bump to pass to other metals. Maybe the first question: why we cannot connect the transistor directly to other elements without all these metallic layers? The question is that all the focus and the cost has been focused on the computation power, on the transistors. The memory, as you have seen also in the example of the hard drive, 250 megabyte drive to 1 terabyte. So the memory industry is also evolving, but not at the same speed and the same pace. So you need to consider the cost of the components before developing them. So that's why we have interconnection layers to have at the end one not costly solution, not costly scale of interconnections. So even these metallic layers has been reduced from a generation to another. So for example, here we take only the interconnection, the metallic layers of 2 process nodes. We will see the process nodes in the next slide. So the 22 nanometer process, we have more than 14 layers. And you can see for the same that the 14 nanometer process has the same number of metallic layers, but with a reduced thickness. So the concept or the principle of miniaturization is conserved also in this shift from 22 nanometers to 14 nanometers. How? By reducing the pitch. The pitch is the size of this metallic via. So it passed from 80 nanometer pitch to 62, and now we are in the era of 2 nanometer process, and the pitch has been reduced also. So by how do we reduce? How do we enhance the quality of the processors and the computation? First, we need to have more transistors, and to have more transistors, we need to have smaller transistors, new architectures, but not only. We need also to work on the miniaturization and more implementation of nanoscale for interconnect. Is this enough? No. So we need also for the metal pitch to reduce it from node to another. So in the upper layer, here you can see the nodes of process of the most advanced silicon process manufacturing node. So we have the 5 nanometer node, 7 nanometer node to 5 to 3, and we are currently some players has started the high volume manufacturing of 2 nanometers node, and all these is coming in the next years. But at some point, we will reach the physical limit. We will not be able to reduce the gate length, as we have seen. The gate is one of the key elements of the transistor. So physically and logically, we will reach some physical limits, and we will not be able to put more transistors in a very condensed area. Here, we need to, the industry need to evolve, and you will be part of this to push from the nanotechnology point of view to develop to meet and solve this challenge for all the industry. So this is the roadmap proposed by IMEC, a research organism in Belgium, with all the efforts of the industry. So if we summarize it briefly, when we pass from a process node of silicon to another, we reduce the pitch, the metallic pitch, which is at the nanometer scale. We need to change we need to nano-engineer the architecture of transistor, which involves also the nano scale. And also in terms of interconnects, we need to reduce the pitch and also change the architectures. We need to change the way how the signal, how the power is being delivered inside these advanced computing devices. So in this slide, in this picture, we can see that in this at the start of this century, 25 years ago, we had more than 25 players able to make transistors in one space. With the time passing from year to another, and when the industry passed from 130 nanometer node to 90 nanometers node, the number of players reduced, and each time we pass to a new generation, new node, the number of players has been reduced. So starting from 2007 to 2019, we have currently 3 players and new Japanese players called Rapidus, able to have this know-how, this knowledge, how to put small transistors with length gates of 10 nanometers, 7 nanometer, and developing them. So we have Intel, Samsung, and TSMC, Taiwan Semiconductor Manufacturing Company. TSMC now is one of the key players, and it has strategic importance even for geopolitics, only by knowing how to handle the silicon at the nanoscale, 2 nanometers nanoscale, and even for the angstrom scale. But we still consider it as the nanometer scale. So, and if we compare at the same time the size of the fab to develop these technologies, we will see that the size of the fab will increase exponentially with the shift of each one, because each new node requires a new fab installation, new equipment, new material used, and of course new design tools. So, for example, if we talk about TSMC has a factory for each node, and they changed when a new process node is proposed. They deleted an old one and replaced the fab with a new fab, bigger, and which is more expensive, and even the equipment are more expensive. To have a quick just give me. We can stop. We can stop whenever you want. Just give me a hint, okay? So this is the supply chain, how our processors are made. So a journey of any integrated chip starts with the design. So we have some fabless companies. They do the design of the processor, the transistors. They send the design to foundries. So foundry is the most important company in the supply chain. They have the ability how to copy or to copy the design to wafers, silicon wafers. And when we prepare silicon wafers, we need to separate them, to dice them, and have each piece of silicon from the wafer. We have it packed, and these are the copper metallic interconnects and the metallic interconnections. Then we have, so this part of packing is made by OSAT, outsourced assembly and test services. And then we have the assembly players. They receive this chip and they place it on a PCB board with other components, passive and active components, and they deliver to the end customer. End customers are like, for example, Apple and others. And to support all these process, we have some IP providers, the companies that they have only the patents. They have the idea how to do it. Then we have some equipment suppliers. So in this case, we have some, for example, for the characterization, how we are able to characterize the nanometers. So we need some advanced equipment. How to do the nano formulation of materials. Of course, you need some suppliers. And in the supply chain of the semiconductors, we have some players. We called them IDMs, integrated device manufacturers. They do everything. Started from the fabless, the foundry, backend, and assembly. To have some examples, we have NVIDIA. You have, of course, you have heard about it, especially in the last years, about AI with all this hype. We have other companies. They do only the design, and they pay other companies to do the processing for them, the manufacturing. We have TSMC, which is today the most important foundry and company in the world. We have Samsung Foundry, Intel Foundry. These companies receive only the design. They made it on wafer, and they give you back the wafer. Then you take it to backend. They take each square of silicon from the wafer with all the design. They pack it and do the metallic layers for interconnection, as we have seen. Then once we have one chip, one IC, we send it to Foxconn and other companies for the assembly, because we will not. If you take, for example, the PCB of a laptop, you will not find only the CPU, but you will have some capacitors, inductors, memory, and others. And we have some IDMs like Intel, ST Microelectronics, and others, IP providers and equipment suppliers. One, you may heard about ASML, which is a Dutch company from Netherlands, which is very important and very strategic. Without the products of this company, we will not have any advanced chip, because they do the photolithography for the 1 nanometer scale. So if you have a design at 1 nanometer, you can copy it. And to have this resolution, we have only ASML able to provide such equipment. So here we have TSMC, which is the dominant in terms of foundries, and it has been evolving from year to another. It is the leader in terms of foundries, TSMC, and we have other small foundries in different countries, but TSMC is the key and the most advanced. They use they have the process, and they have all the tool set that enables TSMC to do the advanced nodes, 2 nanometer, 3 nanometers, coming from ASML and others. But they have also some advanced packaging tools. So the packaging it is another segment which is important. So here, when we have one chip made at 2 nanometer chip, is this enough? No, we need to learn how to pack it, how to handle the chip at the nanometer scale, which is very complex process, and how to support it and how to connect it to this PCB at the end. We cannot put it directly because we cannot put a copper dot of 1 nanometer on a copper circle of 2 millimeters, for example. And connection is bad. So you need some intermediary layers to absorb the difference, the gap, and to be able to connect them. That's what we call the IC substrate or the package substrate. And another way to increase the computation power is to put the chips, the advanced chips, one on the other. So that's what we call the 3D packaging or the 3D stacking. So we have different advanced stacks. We put them, but they have interconnection of the nanoscale. So we need to interconnect them. So this is a new approach to develop advanced products beyond Moore's law. So even we can have higher computation rate compared to Moore's law, developing each year, not each 2 years, but it is not about the manufacturing on new architectures, but how to do the packaging, how we put the chips one on the others. Another concept is the chiplet. So we will see it. So the chiplet is that when the semiconductor industry started, they used to have one piece of silicon inside one chip, one integrated circuit. Then they found that it was not enough, so they added another chip, another silicon piece with the same design inside one integrated circuit. Then they have the same function. This is called the duplication approach. Another approach is the disaggregation. So they put different silicon dies. We call them the dies, the silicon die, but they didn't have the same role, but they had different functions. So for computation, for memory, and etc. So the first one is called the monolithic. We have only one chip. Then with the chiplet, which is the new approach today, maybe if you have purchased a laptop from gaming laptop from AMD, you will see that the marketing is based on chiplet. So for the chiplet, they don't ask one foundry to manufacture the silicon die, but they ask different foundries with different process nodes, and they have put it inside one IC substrate, inside one integrated circuit, the IC, and it has many much better improved performance. This is the chiplet. Another way to develop the performance beyond Moore's law and the number of transistors per the same space. Currently, we are talking about AI. We talk about AI. We talk about ADAS. ADAS is the autopilot driving system. And all these are the most advanced markets. But what is the common point between them is that all these markets, AI, ADAS, high performance computing, we talk about OpenAI for ChatGPT. We couldn't have OpenAI without the NVIDIA chips, the NVIDIA GPUs to do the training. So for example, ChatGPT or OpenAI used more than 4,000 GPUs for H100 GPUs. The one that we will see today, they used more than 4,000 to train their model for ChatGPT 3, ChatGPT 4, and others. Here are the different advanced applications of the semiconductor advanced chips, from AR, VR, biometrics, all these, and each chip include the principles of nanotechnology and nanoscale. The same thing with AI. So AI was not invented in the last years, but its growth started at the same time as the development of the semiconductor industry. But we didn't have the first AI chips until last years, because the semiconductor industry didn't reach the level of performance needed to train and to develop the AI models. At the meantime, the theorists and all the researchers in AI were working on in approaching the AI principles to be able to convert them to hardware. So today we have ChatGPT and we have DeepSeek and others. All these has been pushed and enabled by the semiconductor chips, in other words, by nanotechnology. We talk about AI, but in this we can find some technologies enabling the hardware part of the AI. Here, for example, this is a typical structure of AI accelerator. So accelerator is used for the training or the inference applications for the AI. We can find the PCB, the IC substrate, which is the intermediary. There is another intermediary layer which is called the interposer. So one of the key advantages today of TSMC is that TSMC use some silicon interposers to connect the chips. For example, here you have the GPU at left, and you have the memory. Instead of passing by the IC substrate to connect the information or the data to the memory, you can pass in shorter interconnection. So this shorter interconnection is at the nanoscale, a few nanometers, 10 to 20 nanometers, and it is shorter. So you will have higher speed in terms of GPUs. For example, for the gaming, to have more frames, you need to have advanced chips, and the advanced chips, they use shorter interconnections and the smaller ones. Imagine how, if you have one square of 1 millimeter by 1 millimeter, how many lines you can do if you have a line of 1 millimeter, only one. But if you keep shrinking the length of your pen, so you will be able to do more and more. This is the concept of interconnections, and here we can see that in addition to that, they added many other layers by stacking. That's what we call today the 3D approach in semiconductors. Put in more dies and interconnect them. This is for AI. And this is the next generations. So the intention of the industry is to be able to put more dies or more chiplets inside one IC, one integrated circuit, and to have a bigger IC. It is not easy to develop bigger IC substrates, bigger packages, bigger ICs, because it will require to reduce the pitch, the interconnection length. So you will have more nanoscale content compared to the micro scale content. So a quick example is the NVIDIA product, which is the H100, which has been used to develop to train the model for ChatGPT. So it is GPU, because to do the training of AI models, we need GPUs. The GPU is based on the parallel computing. Compared to CPU is based on each task once a time, but the GPU can do several things in parallel, and that's what has enabled the AI training. If you want to do the training of AI model by CPU, it will take a lot of time compared to a GPU. So this is one of the most advanced GPU. So, and when we talk about GPU, it is not for laptop, PC, personal laptop, but it is used inside data centers. So this is the real size of GPU for data centers. It is much bigger, more powerful, and it consumes a lot of energy compared to the personal use. So this is the size, and this is the inside. This is the PCB. The board, we have different components, but the key component is here is the GPU. Here is the H100. It has more than 80 billion transistors inside and a lot of memory as well. So here we can see that here is the GPU in the middle, and we have HBM or high bandwidth memory just next to the GPU. So it will help to do the processing quickly. So instead of having another memory placed in the PCB, so the interconnections will be longer. So here instead they decided to have the die of the memory inside. And here we have HBM memories, very small, with 60 gigabyte capacity. So, and if we do the cross section, we do the cross section of this GPU, and we can see this is the IC substrate, and we used some advanced characterization tools to be able to see the microscale and the nanoscale. So here at left you can see the HBM memory, which is high bandwidth memory, and here we have the silicon die, the GPU die, and we have some interconnections between them. Here we can see that at the scale of 500 micrometers, we can see this interconnections, and here we have the different dies of memory. So it is very, very small inside. And here we have the stacking of the HBM memory. So only few players are able to do such technology of stacking the HBM. We can have another occasion. We can detail the content and the architectures of the advanced products. So if we do the reverse engineering and all the tear down of this GPU, we are able to detect all the interconnects. So the interconnects in the middle, we can see some of them are at the range of micrometers, 64 micrometers, and the industry is trying to push these measures, these interconnects, to the nanoscale. So if we compare them to the previous generation of GPUs by NVIDIA, for example, we will see that they are at the range of 100 micrometers. But in their roadmap, in the next few generations, they will push them to the nanometers. Of course, not by using the same materials, but more materials and new architectures, of course. This is the FinFET transistor inside. These are the transistors inside the GPU die silicon. So to see them, here the idea of this slide is that you can work on two things. You can work on the processing of nanometers, how to handle them, and there is another aspect. You can work also on the characterization of nanomaterials or nanoscale materials. So here, for example, with the advanced optics and advanced SEM, scanning electronics, and TEM, the electronic microscope, we are able to see 20 nanometers scale of and the architectures of the FinFET. This task will not be easy to do for the next generations and the new architectures based on the GAAFET or the CFET, etc. So even the characterization tool suppliers or companies need to continue to develop their tools to be able to characterize this scale and also to develop it. Because if you are able to process or to manufacture transistors at the 1 nanometer scale, if you cannot see them and test them if they work, you cannot develop the 1 nanometer process. So it is not only about manufacturing, but it is also about testing and characterization. These are the metallic layers. So we have seen the metallic layers for the 22 nanometers and 14 nanometers nodes. And here we can see that these metallic layers are much smaller compared to the 14 and 22 nanometer scales, because this GPU has been processed and manufactured with the 4 nanometers node from TSMC. So NVIDIA did all the design, and they sent the design to TSMC to fabricate it. Just a number about the development of design of H100 GPU design. It has costed more than 10 billions for NVIDIA to develop the design of one GPU, H100. But if we see the economics today, we can see that NVIDIA generated more than 1 trillion of benefits out of this design, and they have even more advanced products for the next generations. And we don't see only NVIDIA in the market, but there are many other players from other countries. So we have talked about AI and high performance computing. This is very important, but there are also many market opportunities and industry opportunities in the electrical cars, augmented reality, virtual reality, ADAS, 5G, 6G. All these represent opportunities for the development and the implementation of the nano solutions. So in this periodic table, so we mainly today we have talked about silicon. We have seen copper in some metallic layers, but the colored elements are the elements that have been used in the microelectronic industry, and you can see that many elements have not been used yet. So for you and for all of us, it represents more opportunities to use all the periodic, many more periodic elements in microelectronics, in nanotechnology, because the performance or the physics at the micro scale are not the same at the nanoscale or the atomic scale. So there are more opportunities, more space to development and to be part of the development of the semiconductor industry for nanotechnology and many other industries. So here we can see most of the many players, important players in the semiconductors. You can see many players, and this list is not exhaustive. There are more than that. But my idea in this final slide is that you can see companies in the US, in Europe, in Asia, but in Africa or Algeria specifically, we don't have such companies. And you have the chance today to be part of this school, nanotechnology and nanoscience school. So it is up to you to put our country on the map of the semiconductor industries and many other industries. I hope I was not very long. Thank you very much for your time and your attention. Thank you very much.
Thank you, Dr. Hashmi, for this inspiring presentation. I want to pass the mic to my colleagues to ask their questions. But before that, I want to ask you my question. Taken into consideration the quantum mechanics limitation, how small do you think a transistor will be in the future? Thank you.
So I would say for the most advanced nodes, it will be for now they are talking about 1 nanometer, and beyond that you can develop it, but to do the mass production, to repeat the process millions of times without having defects, because the defects in the silicon are very important, how to avoid them. So I would say for now 1 nanometers. Maybe they will push for 5 angstroms, but the new generation that will allow to have more computing power is based on photonics. So instead of using electrons, they will pass to the photons, and it will have a new revolution for that.
Does anyone want to ask any questions?
Hello, sir. So I'm just asking, now that NVIDIA has launched a photonics chip not so long ago, like 2 or 4 days, and with the rising of many startups in photonic chips like Lightmatter or Q.ant, do you think that photonic chips will revolutionize the AI chips market, or will it still be silicon even after this?
So yeah, this is a very interesting question. So NVIDIA or Lightmatter, they do not develop photonic chips 100%. They develop what we call co-packaged optics. So they have a photonic engine with the XPUs, with the silicon. So they bring a piece of photonic engine and they put it with the XPU, the CPU or GPU made of silicon, and between them they develop some optical interconnect. So we have been talking about the metallic interconnect made of copper, but the optical interconnects are faster and they enable to have higher speed of computation and higher bandwidth. So it's like you compare the old cables used to connect to the internet, made of copper, and now we have replaced them with fiber optics, and you can see the difference. So it will be the same thing for the co-packaged optics, even for NVIDIA and or Lightmatter or other AI chips. So they, of course, it will increase the computation power, especially in parallel with the photonics, and it will allow to do the training of bigger models more quickly compared to the current products.
Other questions, please? Hello, sir. Thank you for your conference. It was very interesting. My question is there a limitation in the scaling of transistors in the future, since we have already reached the nanoscale and pushing towards the angstrom? Thank you.
Yes, there is physical limitation, but we have the industry has been thinking in one way, but we can increase. So there is a limitation for the scaling, but no limitation for the increase in the performance. We can develop new architectures based on electronics, photonics, even for the quantum. I didn't talk about the quantum today, but even for the quantum, the computation power will be increased exponentially. So there is no limits for the computation, but for the scaling of silicon, we will reach some physical limits and it will be difficult to overcome them.
Thank you, sir. Other questions?
Hello. Thank you so much, sir, for being with us today and sharing your insights with us. I'm grateful for all you've given us. I would like to ask about your opinion as an expert for what are the elements required to be in an ecosystem in order for successful semiconductor startups or companies to emerge?
So I'm not that expert, but thank you very much. It's my pleasure for you to share with you my my insights. And for me, if I go back to the if I go back to the previous. So your question is about this ecosystem, right?
Yes.
Okay. So to enter the semiconductor industry supply chain or ecosystem, we are late. As a country, we are late, but it is we can try always to. There are some efforts from countries like Vietnam, India, and others to enter this market. But how? Which entry point do you want to have? If you want, for example, to do the fabless, if it of course, when we talk about the ecosystem, we are talking about money. You need to have a big investment. So today, to build a new foundry, for example, you need a lot of money, a lot of money, at least $10 billion to build a new foundry with. So you need to build advanced clean room. So the front end is always more expensive because you need all the deposition tools, PVD, CVD. You need expensive tools of photolithography, for example, and the test, the microscopes. All of these cost a lot of money. So it is very difficult for that. For a startup, it is the concept of startup is to have an idea, but you don't have a lot of investment. So except if you develop today a new architecture of transistors and you want to be a startup, you can test your idea of new architectures, but you need to study well the market and the different architectures. For the fabless companies, you can say that I don't develop any silicon content, but I will enhance the design, because not all the circuits are optimized. So you can develop a new design. It will not cost a lot of money to develop a design for a new. Today we don't have only CPU and GPU. GPUs, we have IPUs, we have DPUs, NPUs for neural processing units, so with all the AI, etc. So it is you have less risk to develop a design, or even for the nanometrics. For the assembly, it is low margin business model. You don't have a lot of profit, not a lot of innovation, but you will not need a lot of investment. We have some IP providers, for example, IDEA or Xperi. Their business model is based on developing in the lab new technologies for the future, and then they sell or they license other companies to use their technologies, and they get the benefit from each product. Equipment suppliers, you need you can work on that by developing new process that costs a lot less money and provides better or enhanced performance compared to the existing ones. From the materials, you have more chance in that as well. Some nano fillers, some nano companies, they how to use graphite in semiconductors. You will have an easier access via the material point of view for the semiconductors applications or the fabless as a startup. I have seen many new startups in China and in the US developing new materials nanomaterials for the semiconductors and electronics, and they have been purchased, or they received many fund rounds from different companies to have the high volume manufacturing.
Thank you so much. Thank you so much for your answer. Excuse me a little bit, if I may, I would like to extend my question. Which of these elements do you think could or maybe should be outsourced to another country?
So if we talk about countries, no country has all of them. So today, for example, NVIDIA is doing the design, Taiwan is doing the manufacturing, Malaysia is doing the packaging, assembly is done in India, the equipment is coming from Europe, the patent is coming from the US, for example, the materials are coming from China. Currently, you may heard about all the geopolitical constraints and Huawei issue, for example. So the US is trying to have all this supply chain in the US. So they invented the first transistor, the first integrated circuit, but in the 60s and 70s, they outsourced the manufacturing. They changed the production site to Asia to have low cost of production and higher profit. But now this semiconductor supply chain is a matter of national security. So for the most advanced, because here we talked about the daily use electronics in phones and laptops, but the most important use is in data centers and aerospace and defense. So today, if you want to defend well your country, you need to use advanced chips. If you have the design, who will do the manufacturing for you? Even if you have advanced design, you need to give it to another country to do the manufacturing, and you cannot guarantee that it will not be possessed by others. So the US is trying to have this supply chain in the US. China is trying to do so. US, for example, brought TSMC's advanced factory to Arizona in the US, and they had some problems with advanced packaging, as I said, about chiplet and etc. These are weak points for them. They are trying to invest to convince US players to develop this with investment. China does not have strong EDA tools, electronic design tools. China has some foundries, but they are limited to 12 nanometer, and currently the industry is at the range of 3 nanometers. So in terms of performance, if you compare the performance of a chip made at 2 nanometer, 3 nanometer node, and another one made of 12 nanometers, of course, in terms of in sensitive markets like aerospace or defense, it will cost you a lot to lose this. So this is why the semiconductors are becoming more and more important and gaining more and more market value. And even politicians today are talking about semiconductors. So I hope you will talk about it at least once a week.
So essentially, if I understood correctly, unless you have significant subsidies or investments from the government or from venture capitals perhaps, you cannot really develop all of the elements of the supply chain in-house, and rather the elements should be developed in a country or an ecosystem where the appropriate conditions and materials and so on are available.
Okay, I will share something. For example, if you want to develop 5 nanometer node process, you need at least 20 billions. So imagine this is for one node only, and you don't use one node only. For example, for computing, you need 5 nanometers. For the memory, you need at least 12 or 14. And you need another industry of making passive components like inductors, resistance, and capacitors. You need to have strong software for the electronic design. Today, this is dominated by Synopsys or Cadence. You need also to develop some strong IP to do the assembly. It will take, I think, even the most powerful countries today cannot have all the supply chain. So it is almost impossible to have all the supply chain inside one country. You cannot even have it inside one continent. So it's inside one country is almost impossible.
Thank you. I understood. Thank you so much.
Very good.
Are there any other questions?
Dr. Hashmi, thank you very much for your excellent presentation. Thank you very much for being with us today, for spending more than let's say 1 hour and a half with us. إن شاء الله تكون لك صدقة جارية. We invite you to give us a lecture in physical when you will come to Algeria. Inshallah, the doors of the school are open. Sorry, for you, for your colleagues. If you know some other Algerians abroad, they can help us, or they can give lectures as today. We welcome them to our schools. As you may know, the Thursday is just for conferences, for keynotes, and if you want to give another conference in the future, you will be always welcome. Again, thank you very much for your conference, for your time, and see you inshallah in the next future, inshallah. Thank you very much.
inshallah. Thank you very much. الشرف يعود إلي، وسعيد جدا بلقائكم والمستوى الطلبة. بارك الله فيكم وكل التوفيق إن شاء الله.